All right, folks, we're going to get started. Welcome and thank you for joining our next in a series of webinars, Informing and Inspiring Development of Local Clean Energy and Community Resilience. In this webinar, we are exploring how to maximize the value of electric vehicles, looking towards the road ahead for EVs as grid storage and more. This webinar series is brought to you by Uniting the Central Coast for Action, a growing coalition working to create a resounding voice for climate leadership and resilience on the Central Coast. My name is Eric Vium. I chair the Slow Climate Coalition and am director of Uniting the Central Coast for Action. We have a very exciting program planned for you today. First, a brief primer on EV technology and terminology presented by Michael Hicks, principal of Harmony Building Efficiency Consulting. Then we will hear the status of vehicle-to-grid development in Europe from Paige Mullen, a Central Coast native living in London and managing Nuvi's European vehicle-to-grid operation. And due to the time difference, Paige has been kind enough to pre-record her presentation for us. Next, we will learn about real-world vehicle-to-grid benefits from case studies and simulations at UC San Diego, presented by Dr. Jan Kleissl, professor at UC San Diego in Mechanical and Environmental Engineering, and director of UCSD Center for Energy Research, and director of the UCSD DER Connect National Science Foundation Research Facility. Finally, Dr. Jose Torre-Bueno, executive director at the Center for Community Energy, will explore with us how grid-connected vehicles can be a solution to California to meet our renewable energy goals and benefit grid reliability and resilience. Please ask questions in the chat when speakers are talking, and Barry Rands, the Slow Climate Coalition EV specialist, will answer as many of those questions as possible. And then at the end, we'll address questions that are directed towards the speakers after the presentations are complete. And then if we have time, we'll open up the floor for additional questions, and the questions that we don't get to, we will address in writing. And then finally, we'll take the last few minutes to solicit your feedback and then announce the next webinar and wrap up today's webinar. So before we jump into our program, I want to take a moment to thank all of our fantastic partner organizations who helped to make this webinar extremely successful. And so without further ado, it's my pleasure to introduce to you Michael Hicks. Go ahead, Michael, take it away.
All right, let me share my screen and get this few slides I got going. All right, welcome everybody. I just wanted to, as we discussed this webinar, we kept kind of circling around a lot of the nomenclature that we're all hearing a lot about these days, the vehicle to everything acronyms, and where that really puts us in relationship to the discussion that we're going to have today and that our presenters are really going to speak to. So I want to just speak to and kind of share a little practical information around the V to everything acronyms, which kind of the V to everything, V to X, V to L, or V to load is really about using your electric vehicle's battery energy source to be able to plug something into it and make use of that energy. The acronyms around V to home and V to business, the V to H and V to B, are both very similar in that you're able to use your stored battery power to supplement your home energy use, or in a case where you're not using very much at that particular time, the grid could actually draw some of that energy back from your battery's vehicle, or the vehicle's battery, back onto the grid. And that can happen both in the home situation and the business situation. The other home and business situation that we're really not going to speak to today is around backup power and resiliency. So that's in the case where the grid is actually down and now you're using your electric vehicle as a resiliency source of energy, like a stationary battery would be, or a backup generator. So I want to just kind of give you a couple of examples of this, ultimately leading into the V to G discussion. So we're hearing a lot about this via the auto manufacturers. You're seeing it on advertisements. You're seeing it on their websites. You see it when you go look up an electric vehicle you might be interested in. They're talking about V to load or V to L. And that's making use of the car's battery storage through the vehicle's inverter to convert it into AC and allow you to plug things into it, whether it's tools or your coffee maker or feeding a load potentially back into your house. When we make the V to home and V to business reference, the top little sort of chart I've shared here, when we're connected to the grid, that's our primary source of power for the load that we're plugging in our home or at our business. The alternate is the vehicle to home or vehicle to business source of power from the electric vehicle. In the first box, we're grid only. In the second box, now there's the connection that's made from our electric vehicle through a bidirectional charger to supply power back to the load. And the center box is where the center is going to be the center of the discussion that our other presenters are going to talk about. The far right box there is now when the vehicle is connected to your load and the grid source is now disconnected. And in the little diagram down below, that yellow highlighted box is an automatic transfer switch. And that's where the grid is now disconnected from your load source and your vehicle is supplying the power through this automatic transfer switch to usually a critical loads panel or an emergency backup loads panel that then would feed appliances and things inside of your home. So some examples of that are really, these aren't examples directly of vehicle to home or vehicle to business. These are using stationary batteries or potentially a generator. So in the diagram on the left-hand side, this is a solar install with as circle number 1. Circle number 2 is the automatic transfer switch that's going to transfer the load off of the grid to the battery storage, or to take it from your solar load, or to take it from your vehicle. And it will supply it to the loads that are connected to circle number 4, which is a Lumen Smart Panel, kind of a critical loads panel. So that's a little bit more technical kind of setup and scenario for a vehicle to home or vehicle to business situation. The image on the right is a more simplistic sort of nuts and bolts type scenario where you've got an automatic transfer switch that's going to allow the load from your generator or your stationary battery or your vehicle to be supplied to the emergency loads panel, and it bypasses and doesn't necessarily go to your main panel. So that leads us to the vehicle to grid scenario, which we're really going to be talking about today. And a couple of things I want to highlight here in this particular images are this requires that your vehicle is able to communicate with the device that it's connected to, that's going to be communicating with the grid itself on when that power can be supplemented and supplied back onto the grid. So there's this communication and interconnection process that's still being fleshed out and tried for how effective and how efficient it can be done. This lower image is to kind of give the example of a business situation where maybe it's a business owner that has multiple electric vehicles that they're able to plug into bidirectional chargers. I should say that really right now, as far as I know, you're only able to purchase unidirectional EV chargers. So in other words, you're only able to provide power from your panel and your grid to your electric vehicle. The bidirectional chargers aren't really on the market right now, although they're soon to be. And as with everything, it's hopefully going to happen sooner than we all think. So with that, I'm going to go ahead and let Eric take back over the screen, and Paige Mullen with Nuvve will give us our first introduction of V2G in Europe. Stop sharing. Back to you, Eric.
Great. Thank you for that, Michael.
Uh-huh.
All right. Let me bring up Paige's presentation and we'll start that.
Paige Mullen. Thank you for having me here to present today. Apologies, I wasn't able to come kind of live and in person. Just with the time difference between California and Europe is a bit challenging, but as a Central Coast native, excited to be presenting on vehicle to grid and what kind of different operations and services are being done in Europe that are slightly different than what is done in the US, and how some of these learnings can kind of cross international borders and help lower kind of total carbon across the networks. If you have any questions at the end, apologies again, I'm not able to be there kind of live through video, but please feel free to send me an email at the end. My name is Paige, as I mentioned. I'm the Business Development Manager for Nuvve, based out of our European office in London. I've been in London now about 5 years. And prior to that, was working in San Francisco on vehicle grid integration. So really looking at what's been done in California and now what's being done in Europe. Nuvve is a global company. We're headquartered out of San Diego, California, but have offices in multiple different areas around the world, and do work across lots of different markets and countries. We've been working in vehicle to grid and R&D now for about 25 years. So some of the first papers and services about using vehicle to grid that came out of the University of Delaware were actually written by one of our founders, Professor Willett Kempton there. And we now have over 16 megawatts under management on 3 different continents, and have been running continuous vehicle to grid services in Denmark for almost 6 years now. It'll be 6 years in September. And these are real fleets, real customers driving every day. And I'll touch a little bit more on Denmark at a later stage. So vehicle to grid creates value by looking at energy savings, so just on that customer side, so charging, discharging based off of a tariff, and then also looking at creating revenues on the other side, so actually participating in these energy markets and stacking all of these services. But in order to understand kind of how to extract this value from different types of vehicles, a lot of it matters as well is how the energy system is structured in that country. So in California and a lot of the United States, the energy supply is predominantly vertically integrated. So one company can own power generation, they'll help manage transmission, finally the lines that go into your house, and you also pay your energy bill to that same company. We're starting to see some more suppliers popping up in California through community choice aggregators, but also through the larger investor-owned utilities such as PG&E, SDG&E, and SoCal Edison. But in Europe and in the UK and a lot of other countries here, is each of these are different companies. So they're completely separate entities that work on just one part of the network. And so this gives a different type of services and offerings you can do, but also different rules and regulations and what partners you need to work with. This can be great in some ways because there's a lot more types of services you can offer to a company because they're not vertically integrated. But on the other side, there's a lot more complexity because each of these companies will do something very different, and that's not always aligned. So it can be very useful in some senses, but also make it more challenging in others. Vehicle to grid and Nuvve's platform works as a virtual power plant. So we'll take what I mentioned earlier, this charging, discharging to create revenues or energy savings. And then we'll also look at the energy markets. And so we'll look at what can be done in matching power generation, so matching with renewable generation on a very large utility scale. We'll also look at the transmission system, so balancing frequency across the national networks. And finally, local constraints on the distribution system. So these are local, right on your street, in a small town, based off of your home. And then finally, it'll be your end consumer. So you have the actual site's energy tariff and on that network. Are there lots of chargers and maybe there's not enough supply on that side? Or do you look at a time of use tariff? And how Nuvve and vehicle to grid really creates values, not just off of just one of these services, but stacking these different services based off of seasonality, such as the winter, you don't have as much solar, or you'll have a different time of use tariff or utilization of your vehicles, such as school buses that might be parked all summer. an individual vehicle might not really have a strong impact on the network, but as we're really scaling up and having hundreds and thousands of vehicles, and for example, in the UK where I'm based, starting in 2030, it will be illegal to sell gas-powered vehicles. So all cars will have to have either a strong hybrid element or be fully electric. And by 2035, all cars will have to be fully electric. And that's coming very soon. And so once you look at that volume of vehicles, you really need to understand how to very intelligently optimize this to make sure that we bring on as much renewables as we want. So lots of sun, solar, and wind, but also making sure that when we turn on our lights, we want our lights to come on or our vehicles to be charged. And that's creating this virtual power plant and making better use of these vehicles that when you look on a street or in a neighborhood, that's almost a power plant's worth of energy parked right there. And Nuvve has been doing this now, so as I mentioned, for about 25 years, but really in the last about 6 years, we've really started to scale up. But each country is very different. So what we do in London is going to be different than we do in California, then Denmark, then Japan. And so it's understanding these different nuances, but also knowing that these are real customers. They have to drive every day. They have to make sure their buses are charged to get students to school, that their packages can be delivered, or that they can go out and do the repairs that they need to do on their municipal fleets and their in their municipalities. And so that's incredibly important, but it's also important that it's very simple. So we typically have where customers will plug in, they'll set what they need their charge to be the next day. So we typically work with fleets. So they may say, all right, at 8 a.m. I need to leave and I need my car to be charged at this % so I can do my daily driving. All this is managed through an app and a dashboard for these customers so they can see 24/7 view of what's happening, what their state of charge is, and be able to make those adjustments as needed for what they need. And so we'll look at kind of what are the values. Once we know what a customer is doing, when they're plugged in, when they need to drive, and how much they need to drive, we'll get this on a large scale and also look at each of the markets to see, can we do smart charging, which is kind of a smaller start-stop? What can we do with a demand response, so kind of signals sent from a utility to pause charging or quickly change the rates in which we charge? And then we'll look at if you can actually go into more of a bidirectional element, again, depending on the markets and the rules and regulations. Are you able to connect a charger to a home and actually discharge it? Which in California, this is really starting to change quite a lot in being able to do this in a large, widespread manner, which is a really exciting to see. Versus in Europe and in the UK, we actually have provisions in connecting vehicles to the grid where they actually can discharge. So again, that needs to be taken into account when you look at what types of services to do. And then finally, this ties in with the full vehicle to grid. So really understanding the difference in these terminologies because they have a strong impact, both based off of regulations, but also on the value proposition. And so vehicle to grid, using these as interconnected storage with vehicles, you're able to participating in larger markets that have higher value, such as the ancillary services market or wholesale markets. We also need to understand the different types of customers. So again, as I mentioned, we primarily work with fleets using Nissan Leafs and Nissan ENV 200s, which is a little van. These Nissan vehicles, just right off the line, they're compatible with vehicle to grid through the CHAdeMO standard. So this makes it very easy because you can use any of these vehicles for vehicle to grid as long as you work within the manufacturer's limits. And this is something we work very closely with auto manufacturers to understand what are the requirements they have for their different make and models of their vehicles, and how can we help them run tests to actually understand what will be done to the vehicles so there's no degradation to their batteries. But I get to go down, typically smaller batteries are going to have a smaller revenue potential. And so when we see kind of the value per unit at a home, it's very exciting to see vehicle to grid. It's good for on an individual customer site, but you start to look at the higher value services as well as the fleet's driving pattern. They're much more predictable in when they need to be available. And if you participate in an energy market, those vehicles need to be there. So as we go down, you typically see with big vehicles, you'll have higher revenue potential, which is one of the ones that Nuvve works on in the US is with electric school buses. And so using bidirectional school buses as energy assets. One of our sites that we have in Europe is in Portugal. It's in the Azores. These are some islands, kind of small islands region connected to Portugal, but it's really right in between the United States and Portugal and in Europe in the Atlantic Ocean. And so there's a lot of variability, but also a lot of grid constraints that they need to manage because they're so isolated from everything else. So we've got vehicle to grid chargers installed there, and look at matching wind generation that they have on this island, but also looking at time of use is a really big one because of the different renewables they have. And what we've seen on these vehicles and for these customers, they can get around 25 to 40 euros per car per month off of their energy bill. So they'll pay the mobility fee, and then based off of their plug-in times, they'll have this value. And then on the other side, we'll work with the utility to understand when they have high parts of wind generation. And instead of curtailing that wind, we'll try to charge those vehicles based off of those signals. And I'll go to one of our sites in Denmark and our operations here. So this is the first commercial deployment of vehicle to grid that's been running for now almost 6 years. So it'll be 6 years this September, which is really exciting for this site. It generates on average in Denmark, we get around $2,000 per car per year in revenues just off of one service. So just participating in the frequency regulation market, which I'll show in just a moment, a little time-lapse video of kind of a day in the life of one of these customers here and how that actually looks in operation. A lot of these customers, and the way we have this structured in Denmark, is they'll pay a flat monthly mobility fee that will cover hardware as well as all of the energy they need to drive. So they'll say they'll drive with an agreement to up to so many kilometers or miles per month and per year, and then that they will plug in at certain times. So we know that they'll be back around 3 o'clock in the afternoon, and they leave around 7 o'clock in the morning. So we know what services we can participate in. And again, this will depend, different fleets will have different patterns, so they might have slightly different fees depending on their driving pattern. So here's a little demonstration and a video that we have of our fleet in Denmark. So this is about 24 hours. So it's a little time-lapse video, and I'll kind of talk through what we're seeing on here. So on the top left-hand graph, where you'll see these squiggly lines, these are the vehicles providing frequency regulation. So balancing the frequency and charging and discharging at certain times. But you can see in the state of charge, which is the percentage in the dials, that they'll be fluctuating a little bit. Most of these vehicles, we charge up to 95 to 100%. Then the vehicles leave in the morning around 7, 8 a.m. They'll go out and drive all day, which is right now you'll see these vehicles are out driving, or some are just connected and didn't leave that day or haven't left yet. Some vehicles will come back around lunchtime, and they'll need to charge back up if they have to go out on another drive, or we'll put them in a sleep mode, which is like a pause mode for power saving. And then as these vehicles will start to come back in the afternoon or charge back up, depending on their driving schedule, they'll come back around 2 o'clock in the afternoon. And you'll see the dials are changing and charging up. Then we start to bid the vehicles in the energy markets, which again, you can see based off of these power fluctuations in the top. So these aren't large volumes, but it's a lot of charging and discharging. Again, all this is done within the manufacturer's warranties of what are the operating ranges for these vehicles. Keep them in vehicle to grid mode through the evening and the nights, late afternoon. And now all the vehicles start to participate in different services for vehicle to grid. And then they'll be done for the rest of the day, and they'll repeat that over again. And so we try to make it very simple for drivers so they know what they can do, but then make sure that we can participate and take the complexity out of it. Before vehicle to grid, we typically need 3 key elements. That's compatible vehicles. So most of the vehicles we use in Europe are Nissans because they're right off the line. They're currently vehicle to grid capable through CHAdeMO, but we're starting to see many, many more vehicles and manufacturers coming out with vehicle to grid functionalities in their vehicles in the next few years. So there'll be a lot more options. And then in the US, we work with electric school buses, so bidirectional school buses to have those compatible vehicles. The other is compliant hardware. So hardware that matches both the requirements to install. So does it meet the inverter standards of California or of the UK or of Portugal or the Netherlands? And so understanding the difference in those compliant hardware is very important. And it also needs to work with the vehicle that it's going. And finally, markets and services. It's great if you've got vehicles and hardware, but what is the value that you can extract out of these? And so this is why there will be different regional variations, and what works in Denmark might not directly work in other markets. And so each market needs to really be looked at on its whole and understanding what are these services and what are maybe the regulations that are coming into play that will impact vehicle to grid and EV connections favorably or negatively. So this is a really important area to be working in, one that we're seeing a lot of movement, but it's also a challenge because policy does move quite slow. And you'll have the auto manufacturing industry, that's another very old legacy systems that are really very rapidly trying to change out their supply chains. And on the other side, we have the energy system, another very old legacy system. And both of these need to deal a lot with safety, reliability to them, and working together on this and trying to align on standards is a challenge and something that I think we're seeing a lot of movement. But again, I think it's going to need to continue and speed up. And both of those overlap to then give you the value of the services that you can do. And so these are things that are starting to evolve. And although in Europe we've had longer services with vehicle to grid, a lot of that comes from strong government support. So about 4 years ago, the British government put out £30 million, so almost $40 million in funding for vehicle to grid technology purely to help develop this. And so those are some of the reasons why we've got some very large projects that are more residential focused through Octopus and OVO Energy, some of these energy companies. Nuvve works more on the fleet side. So you see a lot of different types of services, and I think you'll start to see those coming more to the US. But there's other services and types of offerings that are in the US that we don't quite have in Europe, but we're starting to bring some of that involvement and that knowledge to. One of those is electric school buses. It's a very unique and exciting use case because these buses are both very expensive up front. They run for a long time, very usual driving patterns when they leave, when they come back. They're also parked all summer. In Europe, our peak period, so when we have the most kind of peak pricing, is going to be in the winter because it's much colder up north, although we are in a bit of a heat wave right now, so that may start changing. We'll see that typically in the winter. In the US, where we have to have power shutoffs because of high heat or wildfires, and that pricing and peak period comes typically in the summer, also with air conditioning units. School buses are parked most of that. And if you look at a depot like this one that we have here from this site of all these buses, this is a huge amount of power that's parked there. And so it's a great operation for vehicle to grid. And this is one that Nuvve's been working in the US and starting to roll this out because we can help. And our offering is a little different in the US, again, because of the different services and markets. It can provide full turnkey solution for school districts, so helping purchase the bus, purchase the grants, install the hardware, offer up these services for these buses, both behind the meter, but also in the grid technology to help lower the total cost of ownership and transition to net zero. And so this is one of the exciting things about vehicle to grid is it's very different how it's applied in different areas. And although Europe might seem to have more vehicles in some areas, it's behind in other areas. And I think across the board, both are really starting to change and ramp up. And so we'll start to see a lot more, especially as more manufacturers come out with new hardware that's compliant across the world. But I think you'll also see that maybe a manufacturer might offer vehicle to grid in one area, but not another because of these different standards that are coming into play. But it's very important that warranties are upheld and working within those manufacturing limits to really extract the value and put the most unique and customer-centric offerings forward. Thank you so much for inviting me to share today. And if you please, apologies, I couldn't be kind of live on this, but if you've got any other questions or anything, please feel free to reach out. My email's right here. So thank you so much for having me, and hope you have a wonderful rest of your day.
Well, I'd like to thank Paige for a phenomenal overview of Europe's progress on vehicle to grid. Also, before we move on to our next speaker, I would be remiss if I didn't acknowledge that we have Paige's father with us on the webinar today, Pat Mullen. Pat is a longtime friend and local leader from PG&E here in San Luis Obispo, and a proud father, I'm sure. And so thanks for joining us today, Pat. Okay, so now we are going to move into our next presentation, and this is going to be a presentation by Dr. Jan Kleissl, professor at UC San Diego in Mechanical and Environmental Engineering, and director of what sound like very interesting and exciting centers, the UCSD Center for Energy Research and the UCSD DER Connect National Science Foundation Research Facility. And so without further ado, let me activate Jan. All right, Jan, I'm asking you to unmute.
Yeah.
Very good.
Thank
you,
Jan.
Jan.
Now. I also shared the link to the slides just now in the chat. So if I'm talking too slow or too fast, you can jump ahead or read up after I do. Yeah, first of all, thanks for inviting me. Actually, I was in San Luis Obispo 2 years ago and had some great time there with some of you folks on the phone here. So it was great to feel the energy and all the achievements that are going on through the Climate Coalition. Today, I'll talk about some case studies at UC San Diego. I'll go through these slides fairly quickly since we're limited on time, but happy to take more questions later. So we really have fortunate here because we have our own microgrid where we are like a small city. But unlike a city, we don't have a parliament that needs to be convinced to allow things to happen. We have a chancellor who can single-handedly permit many things that take much longer time elsewhere. So it's a small city because it's a large population, 50,000 people, of course, heavy in research and medical institutions. So we have high energy density, yet we want to be carbon neutral and low energy as soon as we can. We have lots of buildings and we have a very high peak electricity use. Here's some of the examples of the technologies we have on campus that are operating. Of course, lots of solar panels. We have a cogeneration facility for natural gas. We have thermal energy storage tanks that can help us reduce the peak electricity use in the evenings and afternoons. We have some large battery systems. We have a fuel cell that's run off of biogas. And then we actually operate and own our own distribution system, so we can really act like a small utility company. Here's a typical day and our history of greenhouse gas emissions at UCSD. So left-hand side, you see by year the greenhouse gas emissions by scope. So for example, scope 3 includes the travel from commuting. Scope 1 is the local emissions. And so we see here a downward trend, but we're still a little ways away from getting to zero. And the right-hand side, you see the energy use and energy supply. So here's the total demand over a typical day at UCSD. And then we see how we have some base load like gas turbine, steam turbine. We have some imports from the SDG&E grid. And then we have solar and storage that help us to reduce some of the peak demand here. Now moving on to EVs. This is our EV claim to fame here. So we started early on with the first EVs around 2015. And here you see the last 7 years of how much megawatt hours we dispensed to EV chargers. So we grew rapidly here. Different colors are different suppliers. One of them actually is Nuvve here in brown. Of course, in COVID, a big drop there, but now we're back over the demand pre-COVID. And this actually is the largest EV demand of any university in the country. So there have lots of EVs here at UC San Diego. Some numbers on charging stations. So we have now 19 DC fast chargers. We have about 360 level 2 chargers. We have 2,400 faculty, students, staff that use these charging stations. And as I'm sure you read from the news, lots of people are now buying EVs. So we have a large plan for build out of more charging stations. What's interesting also historically is that we lost some customers there after COVID. So here you see the same graph that I showed before, but now you see in color actually when people first plugged in. And so, for example, the green would be the 2017 users, and you see they were pretty loyal until COVID hit. After COVID, we lost about half of that demand from these users. So it's hard to say whether they stopped driving to campus or they now charge more at home than on campus. But what is nice to see is that in terms of the new world of high gas prices and interest in EVs, so here now we have actually about 68% of our demand is coming from people who first connected to our network in 2021 and 2022, and that trend probably will be increasing even more, so that the demand is very high, demand for charging and demand for EVs. Here's a typical daily profile of charging that's based on what we call dumb charging, or just charging at full power when you plug in. And we see that at most workplaces, we have people plugging in the morning on the 7 to 9. So we have peak charging around 9 o'clock, and then it tapers off throughout the afternoon and evening. Now, on today's grid in California, we really want to avoid charging during this time here, which means we want to shift the 4 to 9 p.m. Charging to earlier or later. And also here, actually, in the early morning, we want the later charging to happen more in midday, around 10 to 2, when we have the highest amount of solar power on the grid in California. Okay, with that background, some examples here through actual case studies in commercial buildings. We have here 3 applications. One is demand charge management. That's the biggest focus here today. Then renewable energy time shift and resilience. That is not covered today because really for commercial buildings, it's really hard to back up the building just from EVs. So it's not relevant so much for our use case here. So demand charge management, what is that? That means that you have a pre-existing demand from your building, and the utility charges you just based on the peak of that demand, which means that all the other times are irrelevant. Just this time here, which is the highest demand, that will drive parts of your bill that you pay to the utility company. Those so demand charges are common throughout California. So every utility has them in California. And so like the goal is here, can we reduce that peak down to flatten this out better? Then we reduce these demand charges. Here we see a benefit of V2G, right? Because V1G means you can only charge the vehicle. This means you can never actually drop load from this curve. You can only spread out the load more evenly, so it's more flat. So you just avoid higher peaks. With V2G, you can actually decrease the demand charge because you can discharge. And so that means if you discharge right here, then you could actually flatten this peak time here. That's the value of that is about $25 per kilowatt for the non-coincident demand charge. So in the next slides, then we'll see a V2G real case study. I'm going to state the results here up front already. We'll have about $800 a year per EV in savings with this trial that we did here. And in the second part, I'll show some simulations where in this first case, we only had 5 EVs. We weren't operating them very optimally some of the time. So here in the simulation case study, we can see if everything was operating perfectly, we had lots of EVs, what's possible there and what maybe is no longer possible because we have too many cars now. So here's the real case study for demand charge management. We chose a parking garage that has energy use mostly from elevators and lighting. And then we had 3 V1G chargers with BMW cars and 2 bidirectional chargers. As was mentioned before, they're not commercially available yet. So we had some pre-commercial chargers here that were connected to Nissan Leafs. And so we then basically try to drive that charging, discharging to reduce the building peaks. These are just showing you the results in the dollar savings per month for about a 1-year period, month by month. And so you see here, we saved about $100 to $500 of demand charge costs per month over that year. It's highly variable because sometimes you may not have any vehicle connected when demand happens, so you cannot reduce it. Other times you're hitting it right on, so it's quite fluctuating and quite tricky to get that savings. Here you see the actual demand charge cost, which is the original building load. This is what we would get if we had unmanaged charging, and then this was the cost we have with the managed charging. And so these red bars here are difference between the unmanaged charging, which is a simulated signal, and the actual managed charging that we observed with the vehicles. So that was one case study. I mentioned there were complexities of operating all of this in real life. So here's also a simulation study where we used real building data, but we simulated connecting the EVs, and we simulated actually charging, discharging the EVs at the right time. And here, so we were able to achieve the perfect scenario of perfect discharging at the right time. Here the assumptions, we had 1 to 18 EVs connected. We had a long layover, which is typical for a medical worker shift. We had these types of batteries of the EVs. Initial state of charge was half empty. And then we compared the V0G, which is dumb charging and full power, V1G and V2G. Here's actually, you can see better what actually happens when you do this controlled charging. Here with V1G on the left, V2G on the right. Here we see the overall trend for the demand charge. So this shows you one day, and the highlighted areas here are the area of peak demand in red. So here we have higher energy costs, and this is the off-peak demand. And then here you see in the lowest line, that's the actual building load for that building, which was a classroom, an office building. And now the other colors here that go up, those are what happens to the load if we add more EVs. So we start at 1 EV, that's a 24 kilowatt hour load. That's the blue line here, very close to the original line. But then you see we add more and more EVs. And so we see now what happens in V1G. You basically try to charge only during the off-peak time. So we are basically ramping up this demand here. We're not adding anything here in the peak time. We're also trying to flatten things out. So basically have this original peak. We try to accommodate all of the EV load to not increase that peak. And we can do that until 192 kilowatt hours, which is the black line here. At that point, we're still right at the original peak, but now it's all flattened out. Now, as we add more EVs, then of course we can no longer maintain the original peak. Now we're adding demand charge. Whereas V2G, we can discharge, right? So it means that we actually have this original peak here, but now with the first few cars, we're actually not able to drop down that peak. So this is these lines here. You see the black line is 48 kilowatt hours. The green line is 72 kilowatt hours of 3 cars. So these are all quite a bit below that original peak. So now we're actually reducing demand charge. Now, once we add too many cars, in this case, we have 7 cars, then actually we can no longer do that because now we have so much additional charging demand that if we reduce the peak, we'd have to increase the peak somewhere else. So now we can only do a flat load during that time period. So that's the conceptual overview. And here we see the actual numbers, how those work out. So here's the EV charging demand from 0 to 250 kilowatt hours. So roughly from about 0 cars to 15 cars. And here's the cost of electricity for that building. So for V0G, you see it goes straight up because we're really just adding a lot of demand charge because of a short charging window. V1G, it also always goes up, but much less than V0G because you're now charging at the right times when you don't increase as much load, and you're distributing the charging over the entire layover period. V2G, you can decrease the costs in the beginning. So if you have up to about 5 cars here, we actually can lower the cost. Then once we have more cars, actually we're increasing costs, and we're actually not that much better than V1G for large amounts of cars. Here's the same for different buildings. So of course, this all depends on the original building load. And so we have used here 14 buildings, 14 real loads. This is V0G. We see it's very similar trend. All buildings decrease about the same amount. But with V1G, you see some buildings increase earlier and some buildings increase less. And that's because some buildings basically have a peak demand that's actually outside the EV layover window. Now the buildings have a smaller difference between the peak and the average. And so that all drives how much increase in cost you see. Same for V2G. In some buildings, actually, there's almost no reduction in costs. In other buildings, you get a big reduction in cost. So really, this shows that it's actually quite important to model your specific building if you're thinking about implementing V1G or V2G charging. So in summary, if we take all of that together, we had about $800 a year per EV in savings for the real case study. For the idealized case studies, if you compare V1G to V0G, we had $0 to $1,600 per year, an average of about $800 a year in savings. And then V2G benefit over V1G, that would be about $1,800 a year on average in savings per car. So we can see that's quite a bit of savings. Those are the highest you can achieve. So likely the real would be a little bit lower, but still it's quite a substantial amount of money that could be saved there. So the second use case is renewable energy time shifting. That really means let's charge the cars from solar power. So let's charge during midday. Let's avoid charging in the early morning and avoid in the evening. Here you see a typical load profile for a building. So here's the PV generation in blue. Here's the building load in green. Then red is the net load. So we see actually in this building, we exporting energy during midday because we have more PV production than we have consumption over here. And then here's an example EV charging profile. We want to only charge when we have exports to the grid. which means we are avoiding exports and rather consuming energy locally, solar energy locally by these EVs. Setup was similar, parking structure with solar power on it. We had all these cars connected, some V1G cars, some V2G cars. And here we see the greenhouse gas emissions that we quantified here only for 4 months. So we see the greenhouse gas emissions if we had uncontrolled charging, and then the emissions that we saw when we used the V1G and V2G controlled charging. And we see actually quite substantial savings here. So we are roughly cutting the greenhouse gas emissions in half if we use a better charging strategy. So last slide here, more of a application slide to talk about, well, what applications actually are the best for these types of scenarios. So what works best for demand charge management? That's if you have commuters that come to campus or to an office building that have long layovers, meaning you can shift charging around. And especially if the commuters come in the afternoon, because afternoons is typically when most peak demands happen. So if they're around at that time, then you can reduce the peak demand. Best, but the most best, it's still good if you have fleets, but fleets with long layover time. So if you have only people who stay over half an hour for lunch breaks, that's not good. So you have to have fleets with long layover times, and the layover must overlap with the peak load. Bad is if you have fleets with short layover times, because you have no flexibility of charging. You have to charge full power to keep the vehicles operational. And also it's bad if the layover does not coincide with the peak demand. The worst is home charging, because home charging, there are no demand charges, so there's no opportunities for savings if you do home charging. Then for CO2 reductions, what's best there is have fleets with long layover times and layovers that are within the solar peak, so 10 a.m. to 2 p.m. That means that you can now preferentially charge during those hours, and then you can discharge during the evening peak when you have the dirtiest grid energy. Here you see the CO2 content of the grid power for a typical day in California. What's also best is working from home. If you work from home, then basically you're plugged in almost all the time, so you have an EV that's almost like a stationary battery, so you can charge again during low CO2 times. What's still good is you have commuters that stay past 4 p.m. What's medium is fleets with short layover times, which means at least you can do some charging during the day. So you don't have to do all the charging at night because you do have a short layover time during the day. And the worst is commuter home charging. If you charge from at home, you'll always be charging during the nighttime here. That means you'll always be charging during high CO2 emissions. Thank you.
Great. Thank you, Dr. Kleissl, for your very informative presentation. In particular, your ending there was very helpful to see those best and worst applications. Now, just to keep us moving here, we're going to move into our next presentation by Dr. Jose Torre-Bueno. And Dr. Torre-Bueno is the Executive Director of the Center for Community Energy in San Diego. He's a green technology scientist and environmental advocate with expertise in battery technology, photovoltaic system, utility rates, and energy modeling. Thank you for joining us, Dr. Torre-Bueno, and please take it away. I will ask you to unmute one more time. Are you seeing the notification? There you go.
Can you hear me now?
Yes.
Good. Okay, so B2G is a method of managing the duck curve, which I'll explain in a moment. Advance here. Yes. So California has climate goals. One goal is to have millions of electric vehicles by 2030. Another goal is to decarbonize the electricity generation. And somewhat belatedly, they recognize the goal of not leaving behind underserved communities. That is not to make things worse for some people. The duck curve is the issue of when there's a maximum demand for fossil fuels. This green curve, this is the energy, total energy in electrical energy in California as a function of time of day. The green curve is the total demand, which reaches a peak in the early evening. The purple curve is the demand from fossil fuels, that is the demand exclusive of renewables. And the issue is that there's plenty of solar energy in the middle of the day, but when the sun sets, the fossil fuel plants have to rapidly ramp up to meet the declining solar energy. And some point, somebody in the energy industry said, well, this is looking like the back of a duck. So that's become a term of art. And everybody who's responsible for managing the grid agonizes over the duck curve and this rapid ramp up of fossil fuel generation in the evening. And that causes problems in the wholesale market for electricity. This graph is the demand versus available power. So the green line is the sum of all the power potentially available from all generators in California that could be turned on. The red line is the total demand on a particular day. The blue line is the wholesale price of electricity at a certain transformer station, which is what a utility would have to pay for any electricity that they didn't already have on long-term contract. What you see is at a moment when the demand gets close to the total amount of power that could be generated, the wholesale price of electricity goes up by a factor of more than 10. So this business about where are we going to get electricity in the evening is a big issue for everybody who manages the grid. So what does this have to do with EVs? Well, the question is, as Jan was talking about, when and where are EVs going to charge? So this graph is from the California Energy Commission. They were asked to model what's going to be like when there's millions of EVs in 2030. And this first graph is their model for what they call unconstrained alternative future, meaning nobody worries about anything. They just charge their electric car whenever they like. And the answer is if people do whatever they want, most of the charging is going to occur in the early evening, which is the worst possible time for loading the grid. The yellow here represents people charging at home with level 2 chargers. And that's going to greatly exacerbate the duck curve. So the CEC tried 2 other alternatives. One is you adjust the rates so electricity for people who own EVs is much cheaper after midnight, in which case there's a huge spike in demand after midnight, and you somewhat moderate the load that occurs in the early evening. As Jan pointed out, the very best thing would be what they call the EV happy hour. In other words, it would be very much better if people charged, this is work, this blue is charging during work hours. That would greatly reduce the charging in the early evening, reduce the charging at night, and move most of the charging into the time when solar power is abundant. So the current policy is right now rates favor charging at night. And the reason for that is it uses idle nighttime generating capacity. It doesn't strain the transmission grid because late at night, the transmission grid has idle capacity. And that could be enforced simply by rate design. The disadvantage is it's encouraging people to charge their cars with energy from fossil fuel plants, because here's a graph of the CO2 intensity per unit of electricity generated is a function of time of day. In the middle of the day, when there's mostly solar power generating electricity, there's the least amount of CO2 per unit of electricity. Early in the evening, when the most inefficient power plants are running, is the most. Even at night, there's more CO2 per unit. So right now, we're shifting charging of electric cars into the late at night, which is not meeting the state's goal of reducing CO2 production. And what's happening now is, so right now you're rewarded for charging your electric car after midnight, but they're already beginning to change the rates to discourage that. So for instance, it used to be PG&E minimal rate for charging an electric car was after midnight. Now it's from 9 a.m. to 2 p.m. In other words, the EV happy hour. So this is the current model, but it's not going to be one in the future. The CPUC's goal is daytime charging, the EV happy hour. Their image is that the utilities will build more green energy in remote areas, upgrade the transmission grid and the distribution grid, and people will charge at work. The advantage, of course, is utility scale solar is the least costly power. The disadvantage is all of the grid will have to be upgraded, and this will become part of the utility's rate base. It also implies that buildings' internal electrical grids will have to be upgraded. And this means massive upgrades. As part of the same study, the CEC calculated if the grid can carry the requirements for public chargers. Every red line on the map is part of the transmission grid that would need an upgrade to meet the requirements for 8 million electric vehicles by the CEC's calculation. And a consulting group that serves utilities did a study along these lines. And their advice to their utility clients was to expand their revenue streams by entering competitive markets for transportation electrification, meaning EV charging. And somewhat frighteningly, they illustrated this with a picture of a big fish eating a small fish. And that can't make anybody other than the utilities comfortable. Their model suggests that the utilities spend between 11 and 30 billion could be justified in California, which obviously means it's going to wind up in your bill. The original proposal from SDG&E was that all charging infrastructure, including on people's property, should belong to the utility. That got turned down initially. So obviously the utilities, if they got everything they wanted, would own the entire infrastructure all the way to the chargers. And there are certain arguments for this. If the utilities built new infrastructure, you wouldn't have to flow the electricity through the buildings. You wouldn't have to upgrade the panels in the buildings. The disadvantage, obviously, is in the model of the monopoly utility, the more they spend, the more they get to raise the rates. So it means that all this build out of new generation, new transmission and distribution infrastructure, new public chargers winds up in the utilities rate base and is a reason to raise everybody's rates, whether or not you own an electric car. So it's going to mean rate increase for everybody. And the business about, they did in the end get permission to do a pilot project where the utilities installed public chargers. They installed 6,000 level 2 chargers. It came out to $17,000 per charger. Now, given that a charger, a level 2 charger costs less than $2,000, where did the other $15,000 go? It was in what they call make-ready expenses. So the other expenses of bringing power to the location of a charger were $15,000. And that's just for the local upgrades. That's not counting the upgrades to the transmission side of the grid. So that comes out, if you extrapolate that to 1 million chargers, that's $17 billion. That's in line with what the Boston Consulting Group was saying. And if you look at the transmission thing, they've already been allowed to vastly increase their infrastructure spending. Right now, if you look at your bill, there's two parts of it. There's the generation, the transmission, and transmission and distribution. That's typically more than half the bill. So we have a counter proposal. Our counter proposal is, if you want cars charged during the day, the solar collectors should be put where the cars are. That is, we're proposing that in a world where there's millions of electric cars and you want them charged during the day, the EV happy hour, the state should be encouraging the construction of solar arrays over parking lots. The advantages of this, as we see it, are this entire business of upgrading the transmission and distribution system is completely unnecessary. The electricity goes just straight from the solar array into the chargers. The chargers have a very limited connection to the building's electrical panel, so the electrical panel doesn't need to be upgraded. EV owners without home chargers can charge at work. There's a big issue about how people who live in apartments and park on the street are going to charge their vehicles. Well, if charging stations are common at work, that becomes a moot issue. Most importantly, cars can carry charge home to meet the duck curve for owners who have V2H chargers. Bidirectional, that is, if the vehicles are bidirectional, the chargers are bidirectional, this is going to solve the duck curve, which is where I've come to. And this can be built by the owners of buildings. There's no need to involve the utilities. So there's no justification for utility rate increases. Now, the downside of this is that everyone knows, is one of these everyone knows things. Carport mounted solar arrays are about twice as expensive as ground mounts. But we contend that when you factor in the avoided cost of all the transmission distribution upgrades, that makes up for the higher cost of carport mounted solar arrays. So we think that this synergistically solves multiple problems. It eliminates the need to upgrade the grid. For drivers who have a V2X connection at home, it allows them to help tame the duck curve by carrying the excess energy home and discharging into their house to reduce the EVP. For drivers who don't have access to charging at home, it provides charging at work, making EVs possible. The state is looking at the cost of upgrading multi-unit housing, and it's fantastically expensive. And it provides local revenue and keeps funds that would have left the community to the utilities for local building owners. So that raises the question, how much power and energy is available from parked EVs to meet the duck curve? So a back of the envelope calculation, assume there's 5 million EVs, assume their battery capacity is similar to a current Tesla, assume they're charged when they leave work, and that there's a level 2 charger at home. The combined power maximal would be 37,000 megawatts. The combined capacity would be 375,000 megawatt hours. At current prices, this is $52 billion worth of batteries. Obviously, only a fraction of this is going to be available. Well, let's ask what fraction you need. The important thing about personal cars is that they have enormously more capacity than is needed daily, because the average commute is only 30 miles. The people insist that they want an EV that has like 300-mile range. So looking at the duck curve, the maximum discharge that you need to tame the duck curve would be 9,000 megawatts, which is only 28% of the theoretical capacity. The area you need, the megawatt hours you need, is only 12% of the theoretical capacity. So if a fraction of the people who owned EVs in 2030 had bidirectional capable EVs and bidirectional capable charging at home, and were willing to give up a fraction of the power in their batteries in the evening to power their homes, this wouldn't need V2G, it would just need V2H. That would substantially trim the duck curve. The interesting thing is this, there's been numerous pilot projects, but the CPUC is not considering V2G in their future planning as one of the ways of dealing with the evening power necessity. They have a model called the resolve model, which is supposed to come up with the optimal, financially optimal combination of things to do to provide power in the future. The resolve model cannot come up with V2G as a potential solution because V2G is explicitly excluded as a possible solution. So what's come up with is we have to keep fossil fuel plants on standby. We have to buy lots of batteries. We have to import power from other states. But V2G, despite all these pilot projects, the CPUC is effectively operating as though all these pilot projects are going to fail and V2G won't be available even in 2030. And I'm not the only one who thought this. This is a Berkeley study. They simulated 3 million EVs and they were simulating Chevy Volts, which have even less battery, but they come to the same conclusion. The blue curve is the duck curve as it is. The red curve is what happens with what they call uncontrolled. In other words, people charge at the worst time. The green curve is exactly what I'm suggesting. V to G feeding the grid in the evening, and they come to the same conclusion. It basically chops off the duck curve. So our conclusion is utilities and the CPUC are in a path which is going to cost taxpayers and ratepayers tens of billions for new remote generating capacity, new transmission and distribution, and expensive charging stations. There's an alternative, which is local building owners invest in the generating capacity and charging infrastructure, and owners of electric cars provide much of the battery capacity to stabilize the grid just by buying EVs, if these EVs are bidirectional. And all the state has to do is avoid impeding the development of distributed energy by allowing the utilities to expand their monopoly power. In other words, don't implement the NEM3 proposals that are before the PUC that would penalize people for building local solar. So that's what I have to say about V to G as a potential solution to the duck curve.
Great. Thank you, Dr. Torre-Bueno. Let me unpin you, and if you could unshare your presentation. Okay, we're in pretty good time here. I'm going to bring on Barry Rands, the Slow Climb Coalition EV specialist, to ask questions that have not yet been addressed. Barry.
Yeah. Hey, Eric, thanks for letting me share here. I think most of the questions, we've had a tremendous interaction on the chat. There was some discussion about nighttime charging and some battery recycling, and the effect of V2G on warranty, battery warranties, and things like that. I think we got all of those addressed. You had an interesting question yourself, Eric. How is widespread remote work affecting the shape of load curve / EV charging location and demand? That's a pretty good question there. Any one of our panel want to take that one?
Well, Jan had some data on that.
I'll repeat that question. How is widespread remote work affecting the shape of the load curve, EV charging location, and demand?
Yeah, I only have indirect evidence there because we can only basically see people who charge, but we don't know if they left us. We don't know where else they charge. If they charge at home, or if they charge while shopping, or if they sold their EV even, or they're no longer charging because they don't drive anymore as much. Yeah, so from our standpoint, we did lose about 60% of our charging demand because of COVID. So again, where that went, that's unfortunately unknown.
Yeah. I think that basically covers it. If maybe do we have time to open up to general questions from the audience?
Yeah, thanks, Barry. Yes, we do have time to open up. We've got about 10 minutes. If other folks have questions, or there was some other discussion about the proposals around solar over parking lots, and which I think is an interesting, I don't know if it's 100% solution, but I do think it is an interesting solution. It might be, I think it'd be interesting to have some of those questions addressed. And also I'm sharing our co-sponsors just to recognize all of those that have helped to make the event successful today. So if you do have questions, go to the just raise your hand and we can bring you in.
Todd has raised his hand.
Yep, I've asked him to unmute.
Okay. Thank you.
Given the CPUC's apparent siding with the IOUs, the big utility companies, almost in a Stockholm syndrome manner, I think, is there any role that the community choice aggregators can play in this, say the scenario that was just laid out by Mr. Torre-Bueno?
I would hope that they're going to side with the community and oppose the utilities. Some of them have, but not all of them as of yet.
How do they do that practically? Is it by having buyback arrangements with individual power users? Because currently they have to, we users, I'm a solar power generator with solar panels. I put my power out to the internet. SoCal Edison buys that very inexpensively. It turns around, jacks up the rate, send it to the local CPA, Clean Power Lines in LA, who then jacks up further to sell it back to me as 100% green power user from the grid. So I'm trying to cut that ugly train of inflation kind of at the source and go straight to the CPA for my solar panel generation. But are the local aggregators even able to do that? Are they subject to the CPUC tariffs and their priorities to keep the IOUs in monopoly state?
There's some very complicated stuff there because they're not as regulated by the CPUC as utilities, but they're partially regulated by the CPUC. And there's this complicated thing that the utilities own the power lines so that you're still paying the utilities for the transmission. And there's this, this business that you're effectively charged a fee for not being a utility customer anymore. And the CPUC gets to set that fee. And that fee greatly reduces the value of a CCA. So there's a lot of sort of stacking the deck against them by the CPUC. There really has to be a reform of the CPUC to really achieve green power in California. You're totally right about the CPUC being captured.
Practically speaking, Todd, like, independent of some of these barriers, like community choice programs can definitely play an active role in program design and their procurement to, to develop these sorts of technologies, and to be leaders in pilots and in deployment of, again, technology, distributed energy resources, et cetera, to help accelerate this through California. Let me move now to Elsa for her question.
Hi, yeah, I just had a quick question on lithium. My understanding is that most of the EVs use lithium, and just considering kind of how ecologically destructive the mining is, especially in sovereign indigenous territory, I'm wondering if anyone could speak on that kind of resource consumption.
I can say a little bit about that. There are different ways to mine lithium, but the most optimistic thing about that is actually here in California, some of the thermal energy plants, the geothermal energy plants, the hot water that they bring up to generate energy actually has lithium in it as effectively an impurity. It turns out that if you extract that lithium before you pump the water back into the earth, you actually have a byproduct which is saleable. So some of the geothermal plants in the Salton Sea are becoming converted to extract lithium. And that, in terms of footprint, that has an enormously smaller footprint than an open pit mine for lithium. Or the other way of making lithium is to evaporate lithium rich water, which they do in South America. But we're talking about, 1/100th the footprint of extracting lithium from geothermal groundwater. So there are ways of making lithium that are very, very much less impactful than the older methods. So I think net, it will not be as impactful. And remember, the thing about any material that you extract to make an EV, is it something you do once, you make the EV, it drives for a long time, and then when it's done, you can recycle it. Anything you extract as fuel for an internal combustion engine, you have to extract it, it burns, and you have to extract it again the next day. So there's really no comparison.
Thank you, Jose. And Aaron Reeve and Elsa in the chat responded to that with some sources. Amory Lovins and others at RMI have been pointing out the recyclability. Great. So let's move to Michael Saint for your question.
Thank you, Eric. I got on late because I was in another meeting. I hope these aren't not repeated questions, but the first one is, what is Tesla's incentive? You know, they are making pretty much the biggest batteries and are the #1 EV producer. Incentive to make cars that are V2G or V2H when they sell power walls. And on top of that, what do you think is the feasibility of Elon Musk switching to iron instead of the other products to put in their Model 3s presently, and may continue that as well in their other models? Thank you.
Jose, do you want to take the first question?
Couple of things. It's a great frustration that for some reason Musk has taken against V2G.
Yeah.
Some people have the the conspiracy theory that he's against it because he wants to sell power walls. I would think he'd be for it because it would sell more, Tesla vehicles. The battery in a Tesla vehicle is about 3 or 4 times the size of a power wall. But for whatever reason, Musk insists that he's against V2G, and Teslas will not be capable of V2G.
Right.
I would suggest that if other auto manufacturers make V2G, it'll give them a competitive advantage over Tesla, and that may induce them to change. I mean, one disadvantage of a company, which is, the vision and mind of one man, is that if that one person, gets it in his head that they have some decision, apparently nobody in the company can change it. So for the time being, Teslas are not capable of V2G, and they're the bulk of the market at the moment. And that's, to my mind, a big problem. So in terms of iron, bear in mind that iron doesn't replace the lithium, iron replaces the cobalt. And at the moment, it's an iron lithium battery is slightly heavier than a cobalt lithium battery. And so they're using them in the lower performance cars, and they're using the other batteries in the higher performance cars. And that seems to be the general trend in the whole industry. Nobody wants to use cobalt because of the various problems of where it's mined. So most companies are trying to move toward the iron lithium batteries.
All right. Thank you.
Thanks. We have time for, I think, 2 more questions here. Wayne?
Yes. Hi. This question comes from the slide that was about avoiding getting the utility involved with carports and charging cars. I just wonder what you do when you have a number of cloudy days. I mean, how do we manage the lowered output in solar to charge up our cars? How do we avoid that?
The key point I'm making here is that since people insist that they won't buy an EV unless it has 300 miles of range, and in fact, people's average commute is 30 miles, you don't have to charge your EV every day. So if you go and one day there really isn't enough power to charge your EV, it's really not that big a deal. And we're talking, this is a game of averages. It's not a thing, every day it has to happen. On the average, if there's, this huge amount of batteries sitting in all these EVs, on the average, it can substantially reduce the duct curve. That's the key point. If there's a series of cloudy days, then the average load in batteries is going to go down, but that means that if you have to run other forms of generation, you can do it, over the course of the day, not have to run it as an emergency in the evening. So the whole thing gives you sort of more time to manage the grid, even if there's a whole series of cloudy days. It makes it not an emergency that you have to do something over, the course of 3 hours.
Okay. Got it.
Does that make sense?
Yeah.
Just want to point to folks in the chat. There is some really good dialogue here and announcing some events as well in terms of Tesla and B2G and, just thinking about Europe. Let me go to Margarita. Hi, Margarita.
Thank you. Yes, thank you, Eric. And thank you, Jan and Jose. I didn't even catch the first presentation, so this is a great discussion. So given that utilities are our main opponents to propose such a system that optimizes not just cost, but CO2 emissions, I wondered what can we do, the community who really want this to happen? I mean, Jose just said PUC is not even modeling this. Is there a way that we, the community of NGOs can, I don't know, get other champions? Because it seems to me that we're really going to a catastrophe if we really don't implement this kind of solution. With the new EV tax credits, we're going to have hopefully use EVs tax credits. So there will be more EVs on the road. And also I wanted to ask Jan if bidirectional chargers are at cost parity, because maybe that's another way we can reduce the barriers of entry. If everybody has bidirectional chargers, we just maybe have to work with consumers to change their habits, and maybe not changing utilities because they won't change, but we change consumers. So I just wonder our collective wisdom should come up with some strategies to make this happen. Thank you guys. Really great presentations.
Well, one thing you can do is help fight this effort to, tax the sun. I mean, I hope everybody knows about NEM3 and the efforts by the utilities to tax everyone who has solar panels. Look up solarrightsalliance.org. Yes, good. Somebody put it in the chat.
Yeah, I just got, Susan just put it into the chat. Great question, Margarita. I think that's something that I'm thinking about after hearing the presentation, is like, where are the opportunities to engage on this? Because there's a technology and a policy piece of it. And so what can we do to help there? All right, Aaron, you've been patient. You're the last question, and then we're going to move to closing. Yeah, I'm not here. We're not hearing you though. You seem to be unmuted though.
Is that better?
Yes, we can hear you now.
So my question is simply about what is the state of the potential of retrofit for those of us who have electric vehicles that don't have vehicle to grid or vehicle to home capacity? Are we going to just have to wait and buy a new electric vehicle, or is there a retrofit potential there?
Probably not. There was at one point people thought that Teslas actually had bidirectional capacity and hadn't been turned on, but subsequent teardowns of Teslas have convinced people that that probably wasn't true.
Barry, did you have follow-on comments on that too?
No.
Okay,
yeah.
Great. All right, let's pass it over to John Smigelski here for our wrap up.
Okay, so first, thank you all for joining us, and special thanks to the elected officials and staff who was able to join us. We hope you found this conversation to be interesting and inspiring. And thank you to the speakers for their amazing work and taking time to share their experience and expertise with us. And thank you to the co-sponsors for making this event successful. And I want to give a special thank you to the people that helped put this together. Julie Zamek, June Cochran, Barry Brands, and Michael Hicks. We're planning a second part to this series during Electric Drive Week. And on September 27th, we're hoping to have part 2, where we're going to examine some of the new case studies that have been announced and try to get perspectives from utilities, manufacturers, and some additional equipment manufacturers to kind of put it together. But as you see, it's a pretty complex problem with a lot of moving parts, and we hope to keep the conversation going. And if you have any suggestions to us or any feedback, we're happy to hear it. You can send it to me at john@slowclimatecoalition.org, or Barry, or Eric. And again, thank you very much.
Thank you all. And then in closing, we will be, this recording will be shared with all, and we'll confirm with the speakers that we're able to share all of the presentations, but I believe that we have a agreement around that, just to respond to the questions.
And
John?
we'll share this chat and Q&A as well.
Great. Well, thank you all for joining. An excellent discussion. I'm excited for this conversation and just the technology around vehicle to grid, enhancing the way that we're able to address climate and provide value for the grid and for people. And so looking forward to continuing the conversation next time. Thanks all.